The solar system stretches across billions of miles. Yet almost every planet moves around the Sun within the same remarkably thin plane. Why did a three-dimensional cloud of gas and dust become so flat? And what does that shape reveal about our distant beginnings? Tonight, we'll follow the physics behind this quiet cosmic mystery. Before we begin, tell us where you're listening from, and if you enjoy Sleepy Space, please like and subscribe. Imagine rising slowly above the solar system until the Sun becomes a pale point beneath you, and the paths of the planets begin to reveal themselves, not as scattered loops tilted at every possible angle, but as a quiet family of nearly concentric tracks drawn across one broad, invisible sheet. From this distant height, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune seem to circle within the same thin architectural layer. And the first answer to the question of how flat the solar system really is becomes almost startling in its simplicity. It is not perfectly flat, but it is far flatter than a random arrangement of 8 planetary orbits would ever be expected to look. To understand what that means, we must begin with geometry rather than metaphor, because every planet follows an orbit that lies in its own plane, and each of those planes passes very close to the center of the Sun. A plane, in this sense, is not a physical surface and not a force field pressing the planet downward. It is the two-dimensional slice of space traced out by the planet's motion under gravity and inertia. Instead of occupying unrelated orientations, all 8 major planets orbit the Sun in the same general direction, and most of their orbital planes differ by only a few degrees. The familiar reference plane is the ecliptic, defined by Earth's orbit around the Sun. So Earth itself has an inclination of 0 by definition, not because its orbit occupies some absolute cosmic floor. Relative to this plane, Mercury's orbit is tilted by about 7 degrees, Venus by roughly 3.4 degrees, Mars by about 1.85 degrees, Jupiter by approximately 1.3 degrees, Saturn by about 2.5 degrees, Uranus by less than 1 degree, and Neptune by around 1.8 degrees. These numbers already show that the solar system is not a flawless mathematical disk, yet they also reveal how remarkably narrow its planetary architecture remains. 7 degrees may sound substantial, but within the full sphere of possible orientations, it remains a modest departure. The planets, therefore, occupy not a single ideal plane, but a thin bundle of neighboring planes, like pages in a book that have been gently warped rather than scattered across the room. This is where scale becomes important, because a small angle can still produce an enormous vertical distance. At Earth's average distance from the Sun, an orbit tilted by only 1 degree would rise or fall by roughly 2.6 million kilometers from the reference plane at its greatest displacement. And farther from the Sun, the same angular tilt corresponds to a much larger physical height. The solar system is therefore geometrically thin in an angular sense, not literally compressed into a paper-thin layer. Its width is measured in billions of kilometers, while its effective thickness depends on which population of objects we choose to examine and how far from the Sun they travel. The 8 planets define the most orderly version of the disk, while the asteroid belt and Kuiper Belt contain broader spreads of inclination, and the distant Oort cloud is modeled as something closer to a vast spherical reservoir. So even the phrase, "the solar system is flat," must be handled carefully. It describes the dominant architecture of the planets and much of the material that formed near them, not every object held by the sun's gravity. There is also a deeper complication hidden inside the choice of reference plane. The ecliptic is convenient because we observe the sky from Earth, but Earth is only one planet, and its orbit is not the ultimate dynamical ruler of the system. A more fundamental construction is the invariable plane, defined as the plane perpendicular to the total angular momentum vector of the solar system. Each orbit contributes an angular momentum vector perpendicular to its plane, and adding those vectors defines the system's average rotational axis. The invariable plane lies at right angles to it. Because Jupiter is enormously massive and carries a large fraction of the planet's orbital angular momentum, the invariable plane lies much closer to Jupiter's orbital plane than to any arbitrary average of the 8 planetary inclinations. This distinction matters because the planets do not simply orbit on rigid tracks that remain forever frozen in orientation. Their mutual gravity causes their orbital planes to precess slowly, much as the axis of a spinning top turns around a central direction. Over long intervals, the inclination of each planet can vary, its line of nodes can rotate, and its orbital plane can gently weave around the invariable plane, while the total angular momentum of the system remains much more stable. The solar system's flatness is therefore dynamic rather than static. The planetary orbits breathe, tilt, and precess, yet they do so around a common underlying structure. What looks from far away like a motionless disk is actually a coordinated set of slowly changing planes, whose deviations remain limited by the system's shared history and conserved angular momentum. It is equally important not to confuse orbital inclination with axial tilt. Earth's rotational axis is tilted by about 23.4 degrees relative to the perpendicular of its orbital plane, giving us seasons, while Mars is tilted by a similar amount, Saturn by more than 26 degrees, and Uranus rotates with its axis tipped so dramatically that it appears to roll around the Sun on its side. Venus rotates in the opposite sense from most planets, and Uranus also has an unusual rotational orientation. Yet neither fact means that these planets travel around the Sun on wildly separate planes. A planet may spin strangely while still orbiting within the common disk, because axial tilt and orbital inclination preserve different kinds of history. The solar system is flat in the arrangement of its orbits, not in the orientation of every world resting within them. The common orbital direction and low mutual inclinations point back toward a shared rotating source, while the varied axial tilts preserve later events that acted on individual worlds. The planet's slight orbital eccentricities add another layer to the geometry. Each planet moves along an ellipse, so its distance from the Sun changes, but eccentricity describes the shape of the path within its plane, while inclination describes the orientation of that plane in three-dimensional space. Our solar system combines relatively low inclinations with mostly modest eccentricities, making the major planets dynamically calm compared with many mathematically possible configurations, though not perfectly ordered. Mercury is again the most obvious exception among the planets, with both the largest inclination and the largest orbital eccentricity, hinting that the inner solar system experienced a long and complex evolution rather than preserving a pristine primordial pattern. Yet, Mercury's deviations still occur within the broader architecture of the planetary disk, and they do not erase the central fact that the major planets share a remarkably narrow range of orbital orientations. Seen edge-on at a scale our eyes could grasp, the planetary paths would resemble a luminous band with measurable thickness, not a single line and not a sphere. The band would slowly ripple as the planet's orbital planes precess, and each world would move above and below whichever reference plane we had chosen. But the system would remain recognizably disk-like. That geometry is not merely a visual curiosity. It is evidence. The agreement in orbital direction and the small spread in inclination are difficult to explain as coincidence, and far more naturally understood as the inheritance of a common formation environment. The planets were not completed elsewhere and then placed around the Sun. Their masses accumulated from material already moving within a shared, rotating structure. The flatness we observe today is therefore a fossil of motion, a surviving record of the time before planets existed, when gas and dust were already selecting a preferred axis and a preferred plane. But this first chapter leaves us with a deeper question than the one we began with, because saying that the planets formed in a disk only moves the mystery backward. Space itself offers 3 dimensions. Gravity pulls toward a center rather than toward a sheet, and a newborn cloud of gas begins as a volume, not as a celestial plate. So the true puzzle is no longer whether the solar system is flat enough to demand an explanation. It is why a vast 3-dimensional cloud, turning almost imperceptibly in the dark, should ever have become a disk at all. Long before there were planets, moons, asteroids, or even a recognizable sun, the material that would become the solar system occupied a 3-dimensional region of interstellar space, suspended within a far larger molecular cloud where hydrogen molecules, helium atoms, microscopic grains of silicate, carbon-rich compounds, and frozen volatiles drifted through darkness so cold that ordinary human intuition begins to lose its footing. This ancestral material was not arranged as a smooth sphere waiting patiently to collapse, and it was not rotating like a single rigid wheel. Real molecular clouds are irregular, filamentary, turbulent structures, shaped by gravity, magnetic fields, shock waves, radiation, and the restless motions inherited from the interstellar medium. So the region that eventually formed the Sun would have contained density fluctuations, knots, streams, and eddies moving in many directions at once. Yet beneath that local confusion, the entire collapsing region possessed some net angular momentum, perhaps very small when measured against its enormous scale, but not exactly zero, and that slight imbalance was enough to define the future geometry of the solar system. Angular momentum is often introduced through the familiar expression L equals R cross P, where R is the position of a parcel of matter relative to the center of mass, and P is its linear momentum. But the cross product carries more meaning than a compact formula first suggests. It produces a vector pointing along the effective axis of rotation, while its magnitude depends on how much mass is moving, how fast it moves, how far it lies from the center, and how strongly its motion runs sideways rather than directly inward. In a cloud containing countless parcels of gas, each parcel contributes its own angular momentum vector, and many of those contributions partially cancel because different streams move in different directions. Complete cancellation, however, would require an extraordinarily precise symmetry. A natural cloud assembled by turbulent interstellar processes is unlikely to satisfy that symmetry exactly, so after opposing motions are added together, a residual direction remains, quietly selecting an axis long before any planet has begun to form. The origin of that residual rotation does not need to be a single dramatic event. Turbulence can provide it. The shear of galactic rotation can contribute. Neighboring condensations can exert gravitational torques, and asymmetric inflows along molecular filaments can continually alter both the magnitude and direction of the angular momentum entering the collapsing core. Some models also examine whether shock fronts from nearby massive stars could have compressed part of the cloud and possibly influenced the beginning of collapse, although no unique triggering event has been established for the Sun's birth. What matters for the question of flatness is not exactly what initiated the collapse, but that the collapsing material carried a non-zero angular momentum that could be redistributed, yet could not simply disappear. Gravity then began its patient work. When a region becomes sufficiently dense, its self-gravity may overcome the support provided by thermal pressure, turbulence, and magnetic effects, allowing contraction to proceed. In the simplest idealized picture, this threshold is described through the gene's instability, which compares the tendency of pressure to resist compression with the tendency of gravity to amplify a density enhancement. A sufficiently massive or sufficiently cold region has a gene's length or gene's mass beyond which gravity can dominate, but the real path from cloud to star is more intricate than a perfectly uniform sphere collapsing in isolation. Turbulence can both support the cloud globally and create dense pockets locally. Magnetic fields can slow motion across field lines, and material can continue flowing into a core even after collapse has begun. The solar system's parent region was therefore not merely shrinking from all directions like a deflating balloon. It was feeding, fragmenting, exchanging angular momentum, and developing structure while the central density rose. Still, the elementary model reveals the central mechanism with remarkable clarity. As the characteristic radius of the collapsing region decreased, the same angular momentum had to be carried within a smaller space. For a rotating body with moment of inertia I, angular momentum may be written approximately as L equals I omega. And because I falls as mass moves closer to the axis, the angular speed omega must rise if external torques are small. The usual image of a skater drawing in extended arms captures the direction of the effect. Though a collapsing cloud differs profoundly from a solid skater because its gas can flow, collide, heat, radiate, and rotate at different rates in different places. Nevertheless, the cloud's initially subtle rotation became increasingly important as contraction continued. A parcel falling almost directly toward the center could move inward efficiently, but a parcel carrying sideways motion could not reach the center without first losing or transferring angular momentum. As its radius decreased, its tangential speed increased, and eventually its motion bent into an orbit or into a spiraling trajectory rather than a simple radial plunge. This produced what is sometimes called a centrifugal barrier, not a solid boundary and not a mysterious outward force, but a radius at which angular momentum prevents infalling material from continuing directly toward the center. The geometry now began to separate into two fundamentally different directions. Along the emerging rotation axis, material carried relatively little angular momentum around that axis, so it could fall inward with less resistance from rotation. In directions perpendicular to the axis, orbital motion became increasingly important, slowing radial collapse and allowing matter to accumulate. This asymmetry is the first deep reason that a rotating cloud can evolve away from a roughly three-dimensional form and toward a disk. Gravity pulls toward the center in every direction, but rotation resists contraction most strongly in the equatorial region. So the cloud contracts more freely from above and below than it does across the plane. The preferred plane is therefore not chosen by the external universe. It is generated internally, as the plane perpendicular to the net angular momentum vector of the collapsing system. There is no universal cosmic up or down here. Had the parent cloud possessed a different angular momentum direction, the entire planetary system could have been tilted differently relative to the Milky Way, while remaining just as flat within its own local frame. Yet rotation alone does not instantly transform a cloud into a thin disk, and this distinction prevents a common oversimplification. A collection of collisionless particles can carry angular momentum while occupying a thick, three-dimensional swarm of inclined orbits. To flatten efficiently, the protosolar material needed ways to exchange momentum and remove energy, processes that gas performs naturally because it is collisional. As streams converged, shocks converted organized infall into heat. Molecules and dust grains emitted radiation that carried some of that thermal energy away. Magnetic stresses and turbulence transported angular momentum through the growing structure. And some material may have carried angular momentum outward through winds or jets, while other material moved inward toward the forming sun. In the earliest phases, magnetic fields threading the collapsing cloud could couple distant regions and apply torques, a process often called magnetic braking, though its strength depends sensitively on field geometry, ionization, turbulence, and the alignment between rotation and magnetization. Idealized calculations can make magnetic braking so efficient that forming a large disk becomes difficult, while more realistic effects, such as non-ideal magnetohydrodynamics, misaligned fields, turbulent reconnection, and changing ionization, may weaken that braking and allow disks to emerge. This remains an active area of star formation research, reminding us that the broad origin of disks is well established, even while the detailed route by which a particular cloud distributes its angular momentum remains complex. At the center, density and temperature continued to rise until a protostar formed, still gaining mass from the envelope surrounding it. The young sun was not yet powered in the same stable manner as it is today. Much of its early luminosity came from gravitational contraction and the release of energy as material accreted. Around it, matter with too much angular momentum to fall directly inward gathered into a rotating circumstellar disk. Observations of young stellar objects across nearby star-forming regions now reveal such disks as common features of stellar infancy, though their masses sizes, temperatures, substructures, and lifetimes vary widely. These observations have transformed an old theoretical picture into something visible. Dark lanes crossing bright nebulae, rings of millimeter emission, spiral structures, gaps, asymmetries, and broad disks surrounding stars that are still young enough to remain partly veiled by their birth material. Yet the solar system's original disk was not necessarily a quiet, perfectly aligned, smoothly layered plate. Material may have continued arriving from different directions, causing the disk to warp or changing its orientation with time. The protostar and disk could exchange angular momentum through magnetic and gravitational torques. Self-gravity might have produced spiral patterns if parts of the disk became sufficiently massive, and uneven infall could have created temporary asymmetries. The flat structure that ultimately governed planet formation was therefore an evolving average, not an immaculate geometric surface established in a single instant. Its axis emerged from the angular momentum history of the cloud, while its thickness and internal motion reflected the competition among gravity, rotation, pressure, turbulence, and magnetic stresses. The most important transformation had nevertheless begun. A three-dimensional cloud had developed a preferred rotational axis. Collapse had proceeded more efficiently along that axis than across it, and matter, unable to shed all its angular momentum, had collected around the newborn sun instead of falling straight into it. The solar system's plane was already present in embryonic form, not because the planets had aligned themselves, and not because the sun later forced them into order, but because the material from which they would be built had begun separating its motions into those that could be lost, and the collective rotation that had to survive. Still, the disk at this stage remained warm, thick, gaseous, and turbulent, far broader than the narrow orbital architecture seen among the planets today. Something more intimate had to happen within it. Countless collisions would need to erase much of the remaining motion above and below the middle layer, allowing the cloud's memory of 3 dimensions to fade, while its memory of rotation grew sharper. And it is in that slow disappearance of vertical motion that the true physical heart of the solar system's flatness begins to reveal itself. The young solar system did not become flat because gravity pulled everything downward, for there was no universal downward direction to pull toward, and the gravity of the growing sun acted almost radially, drawing matter toward the center from every side. A solitary body moving through empty space could orbit the sun on a plane tilted at nearly any angle and preserve that inclination for an immense span of time. So gravity by itself does not explain why the material around the newborn sun gathered into one broad layer. The crucial difference was that the early solar system was not a collection of isolated planets moving through a vacuum. It was a dense, warm, collisional mixture of gas, dust, charged particles, turbulent eddies, and converging streams. And because those components could strike one another, exchange momentum, generate shocks, heat up, and radiate energy away, the cloud possessed a quiet ability that a collisionless system lacks. It could gradually forget its random motion. To see how this happened, imagine a parcel of gas rising above the disk's emerging middle plane. The sun's gravity does not pull that parcel toward the plane as though the plane were a physical floor. Rather, the vertical component of the sun's gravity pulls it back toward the central region, and near the midplane, that restoring force is approximately proportional to the parcel's height. In the simplest local description, the parcel oscillates upward and downward with a frequency close to the orbital frequency, crossing the densest part of the disk again and again. If nothing resisted it, the oscillation could continue, just as a moon on an inclined orbit repeatedly moves above and below a reference plane without losing inclination. Gas, however, cannot pass indefinitely through other gas without interaction. Each crossing brings compression, drag, viscosity at microscopic and turbulent scales, and the possibility of shock formation when neighboring streams meet faster than pressure disturbances can smooth them. The organized vertical motion is then partly converted into disordered molecular motion, which is another name for heat. That conversion alone does not yet flatten the system, because heated gas may expand again, but the disk can emit radiation, especially through dust grains and molecular processes, allowing some of that thermal energy to escape into space. Once the energy has left as photons, the original vertical motion is not automatically restored. The gas returns toward the midplane with a smaller oscillation, and after many such passages, what began as a thick three-dimensional swarm settles into a thinner, rotating structure. The physical distinction between energy and angular momentum becomes the heart of the process. Energy can be degraded from large-scale ordered motion into heat and then carried away by radiation, while total angular momentum cannot simply vanish inside an isolated system. It may be transferred between neighboring regions, moved outward through stresses, or carried away by winds and escaping matter, but the vector sum must be accounted for. Random motions above and below the disk often contain angular momentum components pointing in opposing directions, so collisions can cancel much of their local disorder, while preserving the system's net rotational motion around the central axis. Two streams moving vertically toward one another may collide and lose most of their opposing vertical velocities. Yet if both are also circling the Sun in the same direction, their shared orbital motion survives the encounter. Repeated across an almost unthinkable number of particles, this selective erasure leaves a system that continues to rotate while becoming progressively less extended in the vertical direction. The disk is therefore not created by rotation alone, and not created by collisions alone, but by their combination. Rotation preserves a preferred plane, while dissipation removes motions that stray too far from it. This is why a cloud of stars in a collisionless stellar halo can remain roughly spherical, even though its members orbit a common center, while a collisional gas cloud can settle into a disk. Stars usually pass through one another's occupied volume without direct contact, so their orbital inclinations are not rapidly damped, but gas particles and fluid streams continually interact. The early solar system behaved as a fluid on large scales, and fluid motion carries information through pressure waves, shocks, turbulence, magnetic stresses, and radiation. Near the disk's midplane, the growing density increased the frequency of interaction, making this region both the destination of settling material and the place where further damping became most efficient. Yet the disk never collapsed into a mathematical surface of zero thickness, because every mechanism that reduced vertical motion was opposed by sources of pressure and stirring. Molecules retained thermal velocities. Turbulence lifted material away from the midplane. Magnetic activity could agitate ionized regions, and infalling matter continued to deliver kinetic energy from the surrounding envelope. A vertical equilibrium gradually emerged in which the downward restoring pull of stellar gravity balanced the upward gradient of gas pressure. In its simplest isothermal form, the gas density falls approximately as a Gaussian with height, and the characteristic scale height can be written as h approximately equal to c sub s divided by omega, where c sub s is the local sound speed and omega is the angular orbital frequency. This compact relation quietly describes the disk's thickness. Hotter gas has a larger sound speed and therefore supports a thicker layer, while stronger vertical gravity and faster orbital motion hold gas closer to the midplane. Because temperature generally decreases outward more slowly than orbital frequency does, the ratio h divided by radius often increases with distance, giving many protoplanetary disks a flared shape rather than the rigid geometry of a dinner plate. Their outer regions rise gently, intercepting radiation from the central star and creating a structure whose thickness is part of its thermal history. Close to the young sun, high temperatures kept many substances in vapor form and raised the sound speed, while farther out, cooler conditions allowed water and other volatile compounds to freeze onto grains, changing the opacity, chemistry, and solid mass available for planet formation. The disk's vertical structure therefore influenced not only its flatness, but also the distribution of materials from which different worlds would later be assembled. The gas was also rotating differentially. Inner regions completed their orbits more quickly than outer regions, following motion that was broadly Keplerian, but slightly modified by pressure support and the disk's own gravity. This shear meant that adjacent rings of gas continually slid past one another, creating opportunities for stresses to transfer angular momentum outward. Ordinary molecular viscosity was probably too weak to explain the full rate at which young stars accrete matter, so astrophysical models invoke larger-scale processes such as magnetically driven turbulence, disk winds, gravitational torques, and hydrodynamic instabilities. The magnetorotational instability may operate where the gas is sufficiently ionized and coupled to magnetic fields. Although large parts of protoplanetary disks may be weakly ionized and governed by non-ideal magnetic effects. Spiral structure generated by the disk's self-gravity could also transport angular momentum during massive early phases. These mechanisms remain areas of detailed investigation, but they share a common consequence. Some material loses enough angular momentum to spiral inward, while other material gains angular momentum and moves outward or helps carry it away. The disk can thus feed the growing sun without violating angular momentum conservation. Its flattening and its accretion are related aspects of the same broader evolution, in which energy is radiated away, while angular momentum is continually redistributed. Even the word collision requires care, because most gas particles collide microscopically all the time, while the most important large-scale dissipation often occurs through shocks and turbulent cascades, rather than through isolated impacts that could be pictured as tiny billiard balls. A supersonic stream meeting slower material forms a shock front where density, pressure, and temperature rise abruptly, converting bulk kinetic energy into heat. Turbulence then transfers energy from large eddies into smaller structures until microscopic processes can thermalize it. Radiation carries some of that energy away, and the disk settles into a new state with less organized motion. Dust grains experience a related but distinct path. Too small to ignore the gas and too massive to behave exactly like individual molecules, they feel aerodynamic drag whenever their velocity differs from that of the surrounding fluid. A grain oscillating vertically through the disk loses energy to the gas and gradually settles toward the midplane, though turbulence can diffuse it upward again. Larger grains generally settle more efficiently until their coupling becomes weak, creating a thin concentration of solids nested inside the thicker gaseous disk. This later becomes essential for planet formation, but the first lesson is already visible. The disk was layered, with gas, dust, heat, and turbulence each responding differently to gravity. Flattening was neither instantaneous nor uniform. It occurred over time, at different rates for different particle sizes, and at different distances from the Sun. The inner disk orbited rapidly and could damp some motions quickly, while the outer disk evolved more slowly. Bursts of accretion, changing magnetic conditions, and continued infall could temporarily thicken or warp the structure. A companion star passing nearby, or uneven flows from the parent cloud, might have altered the disk's orientation, though the specific importance of such events in the Sun's history remains uncertain. What survives these complications is not a picture of perfect calm, but a robust physical trend. Wherever collisional material rotates around a central mass and can cool efficiently, vertical and random motions tend to be damped, while the rotational motion associated with net angular momentum remains. The result is a disk whose plane records the direction of the system's total spin and whose finite thickness records the amount of heat and turbulence it could not entirely lose. The flatness of the solar system, therefore, began not with the planets, but with an enormous sorting of motion. Upward movement met downward movement and was softened. Radial infall encountered angular momentum and was redirected. Heat escaped in faint radiation. Turbulence carried energy towards smaller scales. Magnetic and gravitational stresses shifted angular momentum from one region to another. Across countless orbits, the ancient cloud surrendered much of its three-dimensional disorder while retaining the one organized motion that could not be easily erased. By the time the disk had become a stable nursery for solids, the vertical dimension had not disappeared, but it had been reduced from a dominant freedom into a controlled thickness, a quiet breathing above and below the midplane. And within that narrowing layer, dust grains were beginning to perform an even more delicate descent, settling toward the center of the disk, where the first durable building blocks of planets could gather. Once the young Sun's surrounding gas had settled into a broad, rotating disk, the solids hidden within it began a quieter descent of their own, and this second act of flattening was more selective than the first, because gas and dust did not respond to the disk in precisely the same way. The gas was supported not only by orbital motion, but also by a radial pressure gradient, with pressure generally decreasing away from the Sun, so it could circle at a speed slightly below the purely Keplerian velocity required by gravity alone. A solid grain, however, felt almost no direct support from gas pressure. Left to itself, it would try to move at the faster Keplerian speed, and the difference exposed it to a persistent aerodynamic headwind. That headwind, delicate in any single instant, yet relentless over thousands of orbits, linked the fate of dust to the motion of gas, and gave the disk a way to damp both vertical oscillation and radial freedom. Consider a grain floating above the midplane. The vertical component of stellar gravity draws it toward the central layer, but as it falls, it must push through gas, transferring momentum to the fluid and losing part of its ordered motion. It may cross the midplane and rise on the other side. But each passage is smaller than the last, unless turbulence restores some of the height it has lost. The process resembles a pendulum moving through a thick atmosphere rather than a snowflake landing on a floor, because there is no solid surface waiting below, only a plane of symmetry where the upward and downward components of gravity reverse, and where the gas density reaches its maximum. Dividing the stopping time by the local orbital timescale produces the dimensionless Stokes number, commonly written as St equals t-stop times omega. When St is far below 1, the particle is tightly tied to the gas and responds quickly to every eddy. When St is near 1, it retains enough independence to drift strongly while still feeling substantial drag. When St is much larger than 1, it behaves more like a small celestial body than a suspended grain. The smallest dust particles begin with extremely low Stokes numbers, so they remain mixed through the gas almost as smoke remains mixed through air, while larger aggregates settle more efficiently because they are less easily carried upward by turbulent motions. For particles that remain tightly coupled, the terminal vertical settling speed can be approximated as proportional to minus St times omega times height, a compact expression showing that the descent becomes faster farther from the midplane and slows as the grain approaches the central layer. Yet the midplane never collects every solid into an infinitely thin sheet. Turbulence acts like a diffusive current, carrying some grains upward while gravity and drag bring them down, and the resulting dust layer reflects a balance between settling and mixing. In simplified models, its thickness, h dust, is related to the gas scale height and to the competition between a turbulent diffusion parameter and the Stokes number. Stronger turbulence keeps the solids lofted, while larger, more weakly coupled particles form a thinner layer. Thus, the ancient disk contained nested geometries, a relatively thick atmosphere of hydrogen and helium, a narrower distribution of small grains, and, under suitable conditions, an even thinner concentration of pebbles near the midplane. This sorting raised the local solids to gas ratio, allowing the collective behavior of a dense particle layer to become significant. Before that could happen, however, the grains had to grow, and growth was not a smooth staircase from dust to planet. Microscopic particles could adhere through surface forces when their collisions were gentle, forming porous, irregular aggregates whose internal structure differed greatly from compact rock. Continued impacts could compress them, restructure them, bounce them apart, erode their surfaces, or fragment them completely, depending on composition, size, porosity, temperature, and collision speed. Icy grains beyond the water snowline may have had different sticking properties from dry silicate grains closer to the sun, though laboratory experiments and numerical models continue to refine how large that difference would have been under actual disk conditions. Some pathways encounter a bouncing barrier, where aggregates cease to stick efficiently, and a fragmentation barrier, where turbulent relative velocities become destructive. Even grains that survive face another difficulty created by the same pressure-supported gas that helped define their motion. Because the gas orbits slightly below Keplerian speed, solids lose angular momentum to the headwind and drift inward. The radial drift is often most rapid for particles with Stokes numbers near unity, which in many disk regions may correspond broadly to pebble or larger-sized material, though the physical size associated with a given Stokes number varies strongly with gas density and distance from the star. This inward migration can be alarmingly fast compared with disk lifetimes, producing what is sometimes called the radial drift barrier. Solids may spiral toward the hot inner disk before ordinary pairwise sticking can build them into planetesimals. Pressure maxima, edges of gaps, snowline-related transitions, vortices, and spiral structures can slow or halt the headwind locally, creating dust traps where solids accumulate. Observations of young disks at millimeter wavelengths reveal rings, gaps, crescents, and other substructures that are consistent with strong dust concentration, although the origin of any particular feature may involve planets, changes in opacity, magnetic effects, snow lines, or hydrodynamic processes rather than a single universal cause. Where pebbles become concentrated, their back reaction on the gas can no longer be ignored. A dense stream of solids transfers momentum to the surrounding gas, reducing the velocity difference that caused the drift, allowing still more particles to gather. From this feedback can arise the streaming instability, a family of drag-mediated instabilities capable in suitable regimes of organizing particles into long filaments and compact overdensities. The precise thresholds depend on particle size, pressure gradient, turbulence, metallicity, and the distribution of Stokes numbers. And simulations do not imply that every disk region must undergo the process in the same way. Nevertheless, streaming instability has become one of the leading mechanisms for bridging the difficult gap between loose pebbles and gravitationally bound planetesimals. Once a concentration becomes dense enough that its self-gravity overcomes disruptive shear, particle motions, and gas support, it can collapse into bodies, perhaps tens to hundreds of kilometers across, though the size distribution depends on local conditions and on how the collapse unfolds. Before gravitational collapse, each grain is governed mainly by drag, collisions, and the central star. Afterward, the newborn planetesimal is massive enough to follow a more nearly ballistic orbit, retaining the low inclination inherited from the thin particle layer in which it formed. The solar system's flatness was therefore copied into matter at a new scale. A three-dimensional molecular cloud had produced a gaseous disk. The disk had produced a thinner sediment of solids. The sediment could produce planetesimals already moving on similar orbital planes. At no point did an external force measure their inclinations and place them into order. The geometry emerged through selective survival. Grains that remained in strongly inclined, high-speed motion encountered more gas, suffered greater drag, and spent less time inside the dense midplane where growth and concentration were favored, while grains that settled into the common layer met one another more often and at generally lower vertical relative speeds. Turbulence generated collisions. Pressure structures rearranged material, and local instabilities may have produced clumping long before the disk looked globally calm. Some grains were lost into the sun. Others were shattered and recycled. Some may have been carried outward by diffusion or disk flows, and only a fraction entered the durable planetesimal population. The precise chronology of these processes in the protosolar disk is still reconstructed indirectly from meteorites, disk observations, laboratory work, and numerical simulations, so the broad sequence is more secure than every local detail. Meteorites preserve evidence that the inner solar system contained high-temperature condensates, rapidly formed inclusions, chondrules, and parent bodies that experienced different degrees of heating and alteration, suggesting that transport and assembly occurred in a disk that was chemically and dynamically active, rather than neatly divided into motionless rings. Yet beneath that complexity, the vertical logic remains steady. Drag removed the energy of motion relative to the gas. Stellar gravity repeatedly returned solids toward the midplane. Turbulence prevented complete collapse into an infinitesimal sheet. And concentration mechanisms allowed the densest parts of the particle layer to cross from aerodynamics into self-gravity. By the time the first substantial planetesimals appeared, the original cloud's vast vertical freedom had been narrowed into a small dispersion of orbital inclinations. The future planets would not need to discover a common plane later, because their earliest durable ancestors had already been born inside it. But the arrival of planetesimals also ended the simplest era of settling. For solid bodies large enough to ignore ordinary gas drag would begin stirring one another through gravity, focusing collisions, exchanging orbital energy, and building embryos whose growth could either preserve the disk's calm geometry or disturb it. The next question, then, is not how dust reached the midplane, but how a thin population of newly formed worlds could survive its own increasing gravitational power without scattering itself back into three-dimensional disorder. By the time the first planetesimals had emerged from the dense layer of settled solids, the solar system had already made its most important geometric decision. Because these bodies were not scattered through a sphere around the young sun, but concentrated inside a narrow, rotating disk, where nearly every encounter, every collision, and every exchange of momentum occurred against the background of a shared orbital plane. This distinction changed the entire arithmetic of growth. In a spherical swarm, objects would approach from many directions, often with large relative velocities, meeting only briefly as their paths crossed through three-dimensional space. In a disk, neighboring bodies followed similar paths around the sun, moving in the same general direction and often at comparable speeds, so they remained near one another for longer intervals and encountered one another repeatedly. Their collisions could still be violent, but the initial geometry favored lower relative velocities and more frequent meetings than a random isotropic cloud would provide. The planets, therefore, grew not merely because solid matter existed, but because that matter had already been organized into an environment where accumulation was dynamically possible. A planetesimal circling the Sun possessed an orbital velocity far greater than the small velocity difference separating it from nearby bodies. Near Earth's present orbit, the orbital speed is about 30 kilometers per second, yet two neighboring planetesimals on nearly circular, nearly coplanar paths might approach one another at only a fraction of that speed. What matters for collision is not their full motion around the Sun, but their velocity relative to one another. And this quieter differential motion allowed gravity to reshape their trajectories before impact. As a body gained mass, its escape velocity increased, enabling it to pull passing material inward from beyond its physical surface. The effective collision area became larger than the object's geometric cross-section through gravitational focusing, often expressed by multiplying the physical area by a factor related to 1 plus the square of the escape velocity divided by the encounter velocity. When relative speeds were low, this enhancement could be substantial. When the swarm became dynamically excited and encounters grew fast, gravitational focusing weakened. Growth therefore contained a delicate feedback. A slightly larger body could attract material more effectively and grow faster than its smaller neighbors, entering a phase commonly called runaway growth. Yet as it became more massive, its gravity also stirred surrounding planetesimals, raising their eccentricities and inclinations and making later collisions more energetic. The same gravity that helped the embryo feed eventually heated the population from which it fed. Here the word heat refers not to temperature in the ordinary molecular sense, but to random orbital motion. A dynamically cold disk contains nearly circular, nearly coplanar trajectories, while a dynamically hot disk contains larger eccentricities and inclinations. The early planetary disk was never perfectly cold, but it remained cool enough for growth because several damping processes opposed the stirring. Small bodies continued to feel aerodynamic drag from the gas, which reduced their random motion. Collisions among planetesimals could sometimes dissipate energy, though sufficiently energetic impacts also caused fragmentation. Most subtly, dynamical friction redistributed orbital energy between bodies of different masses. A massive embryo moving somewhat faster or more inclined than the background population gravitationally deflected many smaller objects, leaving behind a slight asymmetry in their distribution that exerted a collective pull against the embryo's peculiar motion. Over time, the massive body tended to lose random kinetic energy, while the smaller bodies gained it, bringing the embryo closer to a circular, low-inclination orbit. This was not friction through physical contact, but a statistical consequence of many gravitational encounters, a mechanism capable of preserving a relatively thin architecture even as large bodies stirred their surroundings. Runaway growth gradually gave way to oligarchic growth, a regime in which a limited number of planetary embryos dominated separate feeding zones. Each embryo influenced a region extending several hill radii around its orbit, where the hill radius measures the scale at which its gravity competes with the tidal field of the Sun. Written approximately as the orbital distance multiplied by the cube root of the planet-to-sun mass ratio divided by 3, the hill radius grows as an embryo gains mass and as its orbit lies farther from the Sun. Neighboring embryos tended to become spaced by several mutual hill radii, creating an ordered sequence of growing worlds embedded within a sea of leftover planetesimals. The disk did not resemble a smooth ring becoming 8 planets all at once. It became a hierarchy of grains, pebbles, planetesimals, embryos, gaps, wakes, resonances, and overlapping zones of influence. Yet this hierarchy remained fundamentally planar because the embryos themselves had formed from the settled layer, and their strongest interactions occurred with bodies sharing similar orbital orientations. The probability of accretion was greatest where paths overlapped frequently, which generally favored objects that remained near the midplane. A highly inclined body spent much of its orbit above or below the dense population, crossing the main layer only twice per revolution, while a low-inclination body remained immersed in the feeding environment almost continuously. Inclination, therefore, influenced not only the appearance of the disk, but the efficiency of growth itself. Bodies that stayed near the common plane encountered more material, and those encounters often occurred at lower vertical speeds, making merger more likely than catastrophic disruption. In this sense, the disk did more than preserve flatness. It rewarded it. Modern models also suggest that many embryos may have grown through pebble accretion, in which centimeter to meter scale solids drifting through the gas were captured after drag removed enough energy during a close encounter. The efficiency of this process depended strongly on the embryo's mass, the particle's stopping times, the local gas structure, and whether the pebble layer was thicker or thinner than the embryo's gravitational reach. When the particle layer was thick, accretion remained three-dimensional, and the embryo intercepted only a small fraction of the passing flux. As settling made the pebble layer thinner, the same capture region could sweep across a larger share of the available solids, making growth approach a two-dimensional regime. The flatness of the dust layer thus became mathematically connected to the speed at which planetary cores could form. This may have been especially important beyond the snow line, where the greater abundance of solid material and the capture of drifting icy pebbles could help build cores massive enough to acquire thick gaseous envelopes before the protoplanetary disk dispersed. The exact importance of pebble accretion relative to planetesimal accretion in the solar system remains an active subject of research, and different regions may have followed different pathways, but both mechanisms begin from the same geometric condition. Solid matter was concentrated into a disk rather than spread through a sphere. The historical nebular ideas associated with Kant and Laplace recognized that a rotating, flattened structure could provide a natural explanation for the planet's common direction of revolution and approximate coplanarity, though early versions lacked the modern physics of turbulence, angular momentum transport, gas drag, planetesimal formation, and numerical n-body evolution. The achievement of contemporary theory is not that it replaced the disk with an entirely different picture, but that it filled the old picture with mechanisms capable of being calculated, simulated, and compared with meteorites, planetary orbits, and observations of young stars. Computer simulations now follow thousands or millions of interacting bodies through phases of runaway growth, oligarchic spacing, resonance capture, scattering, fragmentation, and merger, showing that a thin initial disk can produce a small number of terrestrial planets, while also revealing how sensitive the final architecture is to the distribution of mass and the timing of gas removal. These models do not reproduce the solar system uniquely in every detail, and questions remain about the small mass of Mars, the structure of the asteroid belt, the delivery of volatile material, and the exact migration history of the giant planets. Still, they consistently demonstrate that the geometry of the initial disk strongly constrains what can emerge from it. Growth inside a sphere would populate a wide range of orbital planes, produce a larger distribution of encounter speeds, and make the observed common direction of motion far more difficult to preserve. Growth inside a disk naturally generates worlds that inherit the disk's angular momentum, because each merger combines bodies already orbiting in nearly the same direction. When two planetesimals unite, their resulting orbit reflects the vector sum of their momenta. If both approach from similar planes, the merged object remains close to that plane. Countless mergers, therefore, reinforce the shared geometry rather than erase it. There were exceptions: close encounters, impacts from inclined trajectories, and episodes of substantial scattering. But these acted upon a mass distribution whose angular momentum was overwhelmingly organized around one axis. A single collision could alter a planet's spin dramatically, yet changing the orbital plane of a massive embryo required transferring a much larger amount of angular momentum, usually through sustained interactions rather than one ordinary impact. This is why the final planets could acquire wildly different axial tilts while their orbital planes remained comparatively well aligned. The disk supplied a common orbital framework, while later collisions wrote individual rotational histories onto the worlds inside it. By the end of the main growth phase, the solar system was no longer a smooth sheet of dust, but neither had it become a spherical cloud of independent planets. It had become a thin gravitational society, with embryos and planetesimals repeatedly shaping one another's paths, cooling some motions, exciting others, and gathering mass where the geometry allowed encounters to persist. The planets grew flat because the material available to build them was flat, because low inclination bodies spent more time inside the richest feeding layer, because low relative velocities strengthened gravitational focusing, and because gas drag and dynamical friction repeatedly softened departures from the common plane. Yet the preservation of that plane was not guaranteed. As embryos became more massive, they opened wakes in the gas, exchanged torques with the disk, migrated through one another's resonances, and acquired enough gravity to disturb regions far beyond their physical surfaces. The disk had created the planets, but it now faced the task of controlling them, and the next stage would reveal how the remaining gas acted not simply as raw material, but as a vast damping medium, capable of guiding young worlds back toward the plane from which they had begun. A young planet, embedded in a gaseous disk, did not move through an empty arena, and this simple fact changed the future geometry of the solar system, because every orbit disturbed the surrounding gas, and the disturbed gas responded with gravity of its own. Even a modest planetary embryo raised tides in the disk, compressing gas into spiral patterns that extended inward and outward from its path. These patterns were not decorative wakes trailing harmlessly behind a moving body. They carried energy and angular momentum through the disk, and because the inner and outer regions rotated at different speeds, their gravitational pull on the planet rarely canceled with perfect symmetry. The inner disk generally moved around the sun more quickly than the planet and tended to pull it forward, while the outer disk moved more slowly and tended to pull it backward. The imbalance between these torques could change the planet's orbital radius, producing what is broadly called planetary migration. But the same exchange also acted on orbital eccentricity and inclination, making the disk not only a birthplace for planets, but a medium capable of disciplining their motion. A planet whose orbit remained exactly circular and exactly within the disk's midplane created a relatively symmetric pattern, yet a planet that wandered above and below the disk disturbed the gas asymmetrically. During each inclined orbit, it passed through dense material near the midplane, exciting vertical motions, bending waves, and localized gravitational wakes. The planet transferred some of its vertical orbital energy into the disk, and the gas carried that energy away through waves, turbulence, and dissipation. In reaction, the amplitude of the planet's motion above and below the midplane generally declined. Nothing pushed the planet permanently toward one side of the disk. The process reduced the oscillation itself, so the orbit crossed the central plane at a shallower angle, and reached a smaller maximum height after each cycle. In the language of celestial mechanics, the inclination vector was damped toward the orientation of the local disk. For low-mass planets with small inclinations in a relatively smooth disk, linear perturbation theory predicts that inclination and eccentricity can decay on timescales shorter than the timescale over which the orbit migrates substantially. The exact coefficients depend on the disk's surface density, temperature, thickness, and equation of state, as well as on the planet-to-star mass ratio. But the scaling reveals why the effect can be powerful. A planet repeatedly interacts with a vast amount of nearby gas, and even weak torques become significant when integrated over thousands of orbits. A characteristic interaction timescale often contains the inverse of the planet-to-star mass ratio, the inverse of the local disk mass relative to the star, and the strong dependence on the disk aspect ratio, h divided by r. Because thin disks concentrate mass close to the midplane and produce stronger gradients, inclination damping can be especially efficient there. The mathematics is intricate, but its physical meaning is quiet and direct. The planet gives some of its disordered motion to the disk, and the disk, being extended and dissipative, has many ways to spread and lose that energy. Eccentricity damping follows a related path. A planet on an eccentric orbit alternately moves faster and slower than the nearly circular gas around it, producing changing gravitational wakes and repeated exchanges of momentum. Under many conditions, those interactions reduce the orbital eccentricity, guiding the planet toward a more circular path. Inclination damping and eccentricity damping therefore cool the system in two different dimensions. One narrows the range of orbital planes, while the other narrows the variation in orbital distance. Together, they help explain how a growing planetary system can remain dynamically orderly even while its members gain mass and perturb one another. Yet this order was not absolute, because disk-planet interaction did not operate through one universal formula. The response changed as planets grew. A low-mass embryo generated waves while remaining unable to restructure the disk deeply, a regime usually associated with type 1 migration. In this phase, torques from Lindblad resonances launched spiral density waves at locations where the forcing frequency matched combinations of orbital and epicyclic motion, while corotation torques arose from gas executing horseshoe-shaped turns near the planet's orbit. Depending on temperature gradients, entropy transport, viscosity, and the local surface density profile, these torques could oppose one another, and in some regions, migration might slow, halt, or even reverse. This complexity matters because the disk did not merely drag every planet monotonically toward the Sun. It contained possible convergence zones, pressure transitions, and thermal structures capable of gathering embryos or changing the direction of their radial motion. As planets migrated at different rates, they could approach one another and become trapped in mean motion resonances, where their orbital periods formed simple numerical ratios. Resonant configurations allowed repeated gravitational encounters to occur at protected phases, preventing immediate collision while linking the planet's eccentricities and inclinations. The gas could then damp the excited motion, compressing several planets into a compact, nearly coplanar chain. Many modern models of planetary system formation naturally produce such resonant chains, while the gas remains present, although later instability may break some of them apart. For a more massive planet, the gravitational disturbance became strong enough to repel gas from its orbital neighborhood and open a partial, or deep, gap. Gap formation depended not only on planetary mass, but on whether the planet's tidal torque could overcome pressure, which tried to refill the gap, and viscosity, or other stresses, which transported gas across it. Once a deep gap formed, the planet's evolution entered a different regime, often associated with Type II migration, though modern simulations show that the planet need not simply follow the viscous motion of the gas in a rigid manner. Gas could cross the gap. The planet could migrate faster or slower than a simple viscous estimate, and the outcome depended on the relative masses of the planet and local disk. Inclination damping also changed for massive gap-opening planets. If the planet remained only slightly tilted, interactions with the disk generally continued to favor alignment. But a planet on a highly inclined orbit might spend less time within the dense gas, weakening the damping and introducing nonlinear behavior. Large inclinations could excite warps, shocks, or complicated three-dimensional flows, and in some parameter ranges, the alignment history might become slower or less monotonic. A massive planet could also torque the disk itself, so the question was no longer simply whether the disk aligned the planet, but whether the planet, the inner disk, and the outer disk shifted toward a shared compromise plane. The disk was not an infinitely rigid sheet. Pressure forces communicated warps through bending waves when viscosity was low enough, while in more diffusive regimes, internal stresses smoothed changes in orientation more gradually. If different annuli received different torques, the disk could become warped, with its local midplane changing with distance from the star. A planet embedded in such a structure would tend to align with its immediate gaseous surroundings, rather than with an abstract, perfectly flat global plane. This possibility gives a more realistic meaning to the statement that the disk kept planets flat. It held them close to the evolving plane of the material carrying most of the local angular momentum, even if that plane was gently curved or precessing. The young sun also participated in this exchange. Magnetic connections between the star and the innermost disk, the star's rotational bulge, accretion flows, and any misalignment between the stellar spin and the disk could apply additional torques. Observations of other young systems reveal both aligned and misaligned configurations, suggesting that star disk orientation may depend on the history of infall, companions, magnetic coupling, and internal disk evolution. For the early solar system, the small but non-zero difference between the Sun's equatorial plane and the planet's invariable plane implies that alignment was never mathematically perfect, though the origin of that difference remains uncertain. Still, the planets themselves retained a striking degree of mutual coplanarity, and the gaseous disk offers the most natural environment in which their early inclinations could have been repeatedly reduced. The effect can be understood as a competition between excitation and damping. Planetary embryos gravitationally scattered one another. Resonances pumped eccentricities. Turbulent density fluctuations delivered stochastic kicks, and impacts altered velocities. Against these disturbances, the gas continuously absorbed orbital energy associated with motion relative to the disk. A brief encounter might lift an embryo onto a more inclined orbit, but that orbit would then slice through dense gas twice per revolution, leaving wakes and transferring vertical momentum until the inclination declined. A resonance might increase eccentricity, but disk torques could prevent the growth from becoming destructive. A migrating embryo might approach another planet, yet resonant capture and damping could preserve both bodies inside a narrow layer. The disk acted less like a solid mold than a deep, responsive sea, permitting motion while resisting persistent disorder. Its influence was strongest while the gas remained massive and dense. As the young sun accreted material and radiative heating, stellar winds, magnetically driven outflows, and photoevaporation depleted the disk. The damping timescales lengthened. Ultraviolet and X-ray radiation could heat surface gas until some of it escaped the system, while accretion carried other material inward, and winds removed mass and angular momentum. Observations of young stars suggest that gas-rich protoplanetary disks usually survive for only a few million years, though individual lifetimes vary, leaving a limited interval in which giant planet cores had to capture extensive atmospheres and the entire system could benefit from strong hydrodynamic damping. When the gas surface density fell, planets increasingly interacted with one another rather than with the disk. The medium that had softened eccentricities and inclinations became too thin to absorb their disturbances efficiently. Resonant chains that had been stable under damping could become vulnerable. Neighboring embryos could begin crossing orbits, and close encounters could convert the system's stored gravitational tension into a new era of scattering and giant impacts. The disk had kept the young planets close to its middle plane not by freezing them there, but by continuously removing the energy of every departure while enough gas remained to receive it. Once that quiet restraint faded, the solar system inherited the flat foundation the disk had created. But it also inherited many unfinished worlds crowded into neighboring orbits. The disappearance of the gas would not erase the plane, yet it would allow the planets to wrinkle it, and the next chapter begins at the moment the ancient disk loosened its hold and gravity alone was left to decide how thick the solar system would finally become. When the protoplanetary disk finally began to disappear, the solar system did not lose its flatness all at once. It lost the quiet machinery that had been continually repairing it. For several million years, gas had absorbed eccentric motion, softened orbital inclinations, carried angular momentum through spiral waves, and prevented many gravitational disturbances from growing without limit. But as accretion drew material into the young sun and radiation, winds and photoevaporation removed the rest, the density of that gas declined until the planets increasingly felt one another more strongly than they felt the disk. What remained was still geometrically thin, yet it was no longer dynamically calm. Planetary embryos occupied neighboring orbits, leftover planetesimals crossed their feeding zones, resonant chains stored gravitational tension, and the giant planets may still have been shifting through regions different from those they occupy today. The disappearance of gas, therefore, marked a change in the rules rather than a sudden event in appearance. Before dispersal, motion that departed from the local disk could be damped and converted into heat. Afterward, gravitational interactions mostly redistributed energy and angular momentum among bodies without providing an efficient way to remove either from the system. A close encounter could now raise one object's eccentricity while lowering another's, tilt one orbit while transferring compensating angular momentum elsewhere, or send a small body inward as a larger one moved outward. The total angular momentum vector remained nearly conserved, but the individual orbits were free to wander around it. In this new era, the solar system began to thicken, not because its original plane vanished, but because its inhabitants acquired a growing range of inclinations around that plane. The terrestrial region was probably especially crowded. Numerical models commonly begin with many planetary embryos and a much larger planetesimals distributed across the inner disk, rather than with Mercury, Venus, Earth, and Mars already complete. As these bodies gravitationally stirred one another, their nearly circular paths became more eccentric, and once neighboring orbits crossed, repeated close encounters became unavoidable. Some bodies collided and merged, some were fragmented, some were driven toward the Sun, and others were scattered into more distant regions. The final terrestrial planets emerged through this prolonged phase of giant impacts, likely extending tens of millions of years beyond the first condensation of solids. Each collision combined mass and momentum, but because the impactors did not always arrive exactly within the original midplane, the resulting bodies inherited slightly altered orbital planes and sometimes dramatically altered spins. This distinction is essential. Tilting the rotation axis of a planet requires changing the angular momentum of the planet's own spin, which is much smaller than the angular momentum carried by its orbit around the Sun. A sufficiently oblique impact can therefore overturn a world's axis without comparably tilting its orbit. Uranus may preserve the outcome of one or more enormous ancient disturbances, though the precise pathway remains debated, while Earth's moon-forming impact is widely modeled as a collision between the proto-Earth and another large body, with the exact geometry still constrained by isotopic, dynamical, and geochemical evidence. Such events could make the planets individually strange, while leaving the collective orbital disk recognizable. As embryos grew and the number of bodies declined, the system slowly moved toward greater spacing, because long-term stability favors configurations in which major planets remain separated by enough distance that close encounters become rare. Yet the transition was not a smooth march toward order. Gravitational scattering is strongly nonlinear, meaning that a small difference in the timing or geometry of an encounter can produce a very different final arrangement. One body may receive a small inclination increase, while another is ejected entirely. A resonance may pass harmlessly through one region, but excite another population over millions of years. The solar system's present architecture is therefore one outcome among many physically possible histories, constrained by conservation laws, but sensitive to the sequence of interactions through which those laws were expressed. In the outer solar system, the giant planets exerted the dominant influence. Their masses allowed them to scatter planetesimals efficiently, and every scattered body carried away or delivered a small amount of orbital energy and angular momentum. If a giant planet sent a planetesimal inward, the planet generally gained orbital energy and moved slightly outward. If it expelled material outward or from the system, it could shift in the opposite direction. Repeated over a massive disk of icy bodies, these exchanges could drive substantial planetary migration. Many models suggest that Neptune moved outward through the primordial trans-Neptunian region, reshaping the populations that would become the Kuiper Belt and related reservoirs. Jupiter and Saturn may also have crossed or departed from resonant configurations, altering the frequencies through which they perturbed the rest of the system. The family of scenarios often associated with the Nice model explores how an initially more compact arrangement of giant planets could become unstable after interacting with a planetesimal disk, producing scattering, migration, resonance changes, and the eventual broad structure of the outer solar system. Some successful simulations include an additional ice giant that was later ejected, helping preserve aspects of the surviving four-planet configuration, although this is a modeled possibility rather than an observed historical certainty. The timing, violence, and exact sequence of giant planet instability remain debated, and modern interpretations do not require every older version of a single late catastrophic event to be correct. What these models demonstrate more securely is that the present orbits of the giant planets need not be their birth orbits, and that migration can dynamically heat surrounding populations by increasing both eccentricities and inclinations. Resonances played a particularly subtle role in this thickening. A mean motion resonance arises when orbital periods approach a simple ratio, allowing gravitational perturbations to repeat at similar phases. A secular resonance involves the slow precession rates of orbital ellipses or orbital planes rather than the periods themselves. When these frequencies align, small gravitational effects can accumulate coherently, gradually increasing eccentricity or inclination without requiring a direct close encounter. As the gas disk faded and the giant planets migrated, resonance locations could sweep through the asteroid belt and other regions, exciting bodies that had previously occupied calmer paths. The asteroid belt thus became not merely a remnant of failed planet formation, but a dynamically sculpted population, depleted and stirred by embryos, resonances, planetary migration, and collisions. Its modern spread of inclinations records this complex history, though no single mechanism is likely to account for every feature. The Kuiper Belt, likewise, contains dynamically cold and hot components, with cold and hot referring to the narrowness or breadth of orbital inclinations and eccentricities rather than physical temperature. The cold classical population, in particular, may preserve material that experienced less violent displacement, while hotter populations may include bodies transported or excited during Neptune's migration. These distant objects show that the solar system did not thicken uniformly. Some regions retained thin, delicate substructures. Others were stirred into broad clouds of tilted orbits. The amount of vertical heating depended on local mass, resonance history, scattering encounters, and the presence or absence of damping populations. Even after the gas vanished, leftover planetesimals could continue to provide a weaker form of dynamical friction. Large bodies transferred random energy to numerous smaller ones, helping reduce the eccentricities and inclinations of the survivors, while heating or ejecting the background population. As that population was consumed, fragmented, or removed, the damping weakened, leaving the major planets in a configuration that was calmer than the most violent phase, but thicker than the primordial disk. The system approached stability through loss. Countless smaller bodies absorbed energy, crossed unstable resonances, struck larger worlds, fell toward the sun, or escaped into interstellar space. and their departure allowed the remaining planets to settle into more widely separated orbits. Still, there was a limit to how far the architecture could be randomized. The overwhelming share of planetary orbital angular momentum had begun aligned around one common axis, and internal interactions could redistribute that angular momentum, but could not easily rotate its total vector. For the entire planetary system to become spherical, a vast source of external torque or a succession of extraordinarily disruptive encounters would have been required. Ordinary scattering among bodies born in the same disk tends instead to produce a thicker disk, because the available angular momentum remains concentrated around the original rotational direction. The planets may trade inclination, their orbital planes may precess, and smaller objects may be launched into extreme orientations. But the massive survivors continue to revolve around a common mean plane. This is why the modern solar system resembles a sheet that has been wrinkled, rather than a sphere that has forgotten its origin. Its deviations are genuine and scientifically valuable, yet they remain deviations from a dominant structure established before the planets existed. Even today, the orbital planes of the planets slowly precess under mutual gravitational torques, their inclination vectors tracing gentle cycles around the invariable plane. Over millions of years, no single planet keeps exactly the same orientation relative to Earth's ecliptic, yet the collective system remains anchored by its nearly conserved total angular momentum. The flatness is therefore not frozen geometry, but long-lived dynamical memory. Gas created and maintained a thin beginning. Gravity later heated, folded, and redistributed that beginning without erasing it. When the disk disappeared, the solar system became free enough to acquire scars, but not free enough to abandon its ancestry. The final thickness of the planetary system emerged from the balance between ancient alignment and later disturbance, between a shared origin that kept the massive planets close to one plane and a turbulent youth that allowed smaller bodies to wander far from it. And those wanderers now become the next part of the story, because Mercury, Pluto, the excited asteroid belt, the scattered disk, and the almost spherical reservoir of distant comets reveal exactly how far a system born flat can be bent before its original geometry is lost. Seen from far above, the planets still suggest a calm and disciplined disk. But the moment we look beyond the 8 major worlds, the solar system begins to reveal a more complicated geometry, filled with bodies that climb steeply above the ecliptic, dive below it, or even travel around the sun in the opposite direction. These objects do not overturn the idea that the solar system formed from a flattened disk. They show what happened after that disk lost the power to keep every orbit quiet. The first important example is Mercury, whose orbit is tilted by about 7 degrees relative to Earth's orbital plane, making it the most inclined of the 8 planets. 7 degrees is easily visible in a precise model, yet it remains a small deviation compared with the full range of possible orientations in 3-dimensional space. Mercury has not escaped the planetary disk so much as risen modestly above its central layer, and its orbit also possesses an unusually large eccentricity, carrying it through a more elongated path than the other major planets. Its present motion is shaped by the long gravitational influence of the other planets, especially through secular interactions that slowly alter the orientation and shape of orbits over millions of years. In such interactions, no close collision is required. Each planet applies a faint, repeating torque, and those small effects can accumulate as orbital ellipses and planes precess. Mercury lies in a dynamically sensitive region where resonant relationships among these slow frequencies can amplify changes, although reconstructing one unique history for its present inclination remains difficult. It is a reminder that even a planet born near the disk's middle can drift away from perfect alignment without ever becoming truly disconnected from the system's dominant plane. Farther out, the asteroid belt offers a much broader demonstration of orbital heating. It is often imagined as a narrow, orderly ring between Mars and Jupiter, but its real population occupies a substantial range of eccentricities and inclinations, with some asteroids staying close to the ecliptic and others moving on paths tilted by tens of degrees. The belt was never allowed to become a planet-sized world, not simply because there was too little material, but because Jupiter's gravity, resonances, collisions, and the possible migration of the planets continually disturbed the region. Mean motion resonances with Jupiter removed or destabilized objects at particular orbital periods, helping create the Kirkwood gaps, while secular resonances altered eccentricities and inclinations over longer timescales. Planetary embryos may once have crossed the belt as well, stirring and depleting it before being absorbed or expelled. The modern asteroid belt is therefore not a pristine cross-section of the original disk. It is a surviving population that has been dynamically filtered, with its thickness preserving evidence of repeated excitation. Yet its orbits remain concentrated around the planetary plane rather than distributed uniformly across the sky, showing that the original disk is still present beneath the later disturbance. Beyond Neptune, the geometry becomes richer still. The Kuiper Belt is not a single flat ring, but a collection of overlapping dynamical populations whose orbital structures record different histories. The cold classical objects generally have relatively low inclinations and modest eccentricities, and the word cold refers to this limited, random orbital motion rather than to their physical temperature, which is of course extremely low. Their delicate orbital distribution may preserve material that formed in the outer disk and avoided the most violent stages of Neptune's migration. The hot classical population, by contrast, extends to much larger inclinations and eccentricities, suggesting stronger scattering, resonance, transport, or implantation from other regions. Calling it hot means that its members possess a larger dispersion of orbital energy and orientation, as though the once thin disk had been stirred into a deeper vertical layer. Pluto belongs to a resonant population known as the Plutinos, objects whose orbital periods maintain an approximate 3:2 relationship with Neptune. Pluto completes roughly 2 revolutions for every 3 made by Neptune, and the resonance protects the two bodies from close encounters despite Pluto's orbit crossing inside Neptune's average distance from the Sun. Its inclination of about 17 degrees and its substantial eccentricity are not signs of random disorder, but parts of an organized resonant motion. The orientation of Pluto's orbit and the repeated phasing of its conjunctions keep it dynamically separated from Neptune, demonstrating that a highly tilted path can still be governed by precise celestial architecture. Haumea, with an inclination near 28 degrees, and Eris, tilted by roughly 44 degrees, travel even farther from the original midplane. Their relatively large masses make them especially visible examples, but their inclinations do not imply that the entire outer solar system shares their orientation. They are survivors of a population in which the giant planets, especially Neptune, could exchange enough energy and angular momentum with smaller bodies to lift some onto steep paths, while leaving the total angular momentum of the major planets almost unchanged. Mass matters here. A dwarf planet can be dramatically redirected by a giant planet without significantly tilting the giant planet in return, just as a small boat may be thrown aside by the wake of a ship while the ship's course barely changes. This unequal exchange explains why the solar system can contain spectacular orbital exceptions without losing the flat structure defined by its most massive members. Some trans-Neptunian objects occupy detached orbits whose distant perihelia keep them from strong present-day encounters with Neptune, and a few have been found at extremely high inclinations or even on retrograde paths. Their origins are still investigated through several possibilities, including ancient planetary scattering, resonant evolution, interactions within the Sun's birth cluster, and perturbations from as yet undetected distant masses. No single mechanism has been shown to explain every unusual outer orbit, and the small number of known extreme objects is affected by observational bias because surveys do not examine all regions of the sky with equal depth. Their existence nevertheless shows that the outer solar system has access to mechanisms capable of rotating orbital planes far beyond the gentle inclinations of the planets. Between the Kuiper Belt and the inner planetary region move the centaurs, unstable bodies whose orbits cross or approach those of the giant planets. Their dynamical lifetimes are usually short compared with the age of the solar system, because repeated planetary encounters can redirect them, send them inward as comets, push them outward, or eject them completely. Some centaurs possess high inclinations, and a few follow retrograde or nearly polar orbits. These are transitional objects, wandering through a region where no single planet permanently owns their motion, and their changing trajectories allow us to watch, in numerical models, how scattering turns a once disk-like population into a far more three-dimensional one. Comets carry this process to its most dramatic expression. Jupiter family comets generally retain relatively low inclinations and are commonly linked to the scattered disk beyond Neptune, where repeated interactions gradually deliver some bodies inward. Halley-type and long-period comets occupy a much wider range of inclinations, including retrograde paths. Halley's comet, for example, travels around the Sun in the opposite direction from the planets, on an orbit inclined by more than 160 degrees to the ecliptic. Such a trajectory might seem to contradict the solar system's flattened origin, but it is better understood as evidence that small bodies can have their orbital angular momentum thoroughly reoriented after formation. A comet contains an almost negligible fraction of the system's total angular momentum, so its orbit can be turned over without meaningfully changing the plane of the planets. The source of many long-period comets is thought to be the Oort cloud, a distant reservoir extending perhaps thousands to tens of thousands of astronomical units from the Sun. Unlike the planetary region, the outer Oort cloud is expected to be approximately spherical. This does not necessarily mean its members formed in a sphere. The more widely accepted picture begins with icy planetesimals forming near the giant planets inside the primordial disk. Close encounters with Jupiter, Saturn, Uranus, and Neptune then scattered them onto extremely elongated orbits. Some were ejected from the solar system entirely, but others remained weakly bound at enormous distances. There, the Sun's gravitational hold became so delicate that passing stars, the tidal field of the Milky Way, and perhaps encounters within the Sun's early stellar cluster could gradually alter the directions of their angular momentum vectors. Over immense timescales, these external perturbations randomized the orbital orientations, transforming a population born near a plane into a nearly spherical cloud. The transition can be understood through the changing hierarchy of torques. Near the planets, the gravitational influence of the planetary system defines a preferred local plane, sometimes discussed through the concept of a Laplace plane, around which satellite or small body orbits may precess. At sufficiently great distances, the tidal influence of the galaxy and passing stars becomes comparatively important, and the original planetary plane loses its authority. The farther a small body travels from the Sun, the easier it becomes for the wider environment to reshape its orbit. The Oort cloud is therefore not a rejection of the disk, but the outermost consequence of material being scattered so far that the disk could no longer keep its orientation intact. These exceptional populations reveal a central principle. Formation determines the initial distribution, but long-term dynamics determines how much of that distribution survives. Massive planets remain close to the original plane because altering their orbital angular momentum requires enormous torques. Smaller bodies can be lifted, flipped, trapped in resonances, or dispersed into a sphere because their angular momentum is easier to exchange. The solar system is flat, where most of its mass and orbital angular momentum reside, while becoming progressively more three-dimensional among populations that have been strongly scattered or placed at great distances. Its architecture is therefore layered rather than contradictory. A thin planetary core, dynamically heated belts, unstable transitional objects, and a distant cometary cloud whose nearly random orientations record the influence of the galaxy itself. The bodies that appear to disobey the plane are not outsiders to the story. They are the marks left by everything that happened to the disk after it formed, each inclined orbit preserving a different history of resonance, migration, scattering, or distant perturbation. And yet, one small misalignment remains more difficult to place, because the planets are not only tilted relative to one another, their collective plane is also slightly tilted relative to the equator of the Sun that created them, suggesting that even the central star and its ancient disk did not preserve perfect agreement. The solar system is remarkably flat, yet it is not perfectly aligned with the body at its center. And this small imperfection opens one of the most delicate questions in planetary science. If we define the reference surface by Earth's orbit, the solar equator is tilted by about 7.25 degrees to the ecliptic. If we instead use the invariable plane, the plane perpendicular to the total orbital angular momentum of the planetary system, the misalignment is closer to 6 degrees. The distinction is more than bookkeeping. The ecliptic follows one planet and slowly changes with Earth's orbit, while the invariable plane represents the weighted rotational architecture of the system, dominated especially by the angular momentum of Jupiter and Saturn. The Sun's spin axis, the planetary angular momentum vector, and Earth's orbital normal therefore point in three slightly different directions, like three compass needles that nearly agree but preserve separate histories. In the simplest version of the nebular model, such disagreement should be small. The Sun and its disk formed from the same collapsing material, so the angular momentum that spun up the young star and the angular momentum that supported the disk would be expected to begin nearly parallel. Planets assembled within that disk and inherited its local plane, suggesting that the present planetary system should orbit close to the Sun's equator. This reasoning is sound as a first approximation, but it quietly assumes that the direction of incoming angular momentum remained fixed, that the disk behaved as a rigid sheet, and that the young Sun always responded quickly enough to follow any change. None of those assumptions is guaranteed in a real star-forming cloud. The protostar gained most of its mass through streams descending from an irregular, turbulent environment, and the angular momentum carried by later inflows need not have pointed in exactly the same direction as the material that arrived earlier. If the orientation of accretion changed while the star and disk were growing, the outer disk could have been fed along a new plane while the stellar spin retained more of its previous direction. The result would not require a dramatic collision or a hidden planet, only a slow disagreement between successive layers of infalling gas. Modern observations of young stars increasingly suggest that primordial star-disk misalignment is not exceptional in every system, strengthening the possibility that a modest solar tilt could have been inherited rather than produced after planet formation. Although applying population-level observations to the Sun remains an inference because the protosolar disk vanished more than 4.5 billion years ago and left no direct image of its original orientation. A second possibility begins with the disk itself refusing to remain flat. A protoplanetary disk is held together by gravity and pressure, but it is not a solid plate, so a torque applied more strongly to one radius than another can make its annuli precess at different rates. Pressure forces, viscosity, magnetic stresses, and self-gravity then determine whether the disturbance travels as bending waves, diffuses gradually, or produces a persistent warp. The planet-forming region might have remained internally coherent while being tilted as a whole, or the inner and outer disk might briefly have occupied different planes. Planets forming in one portion would inherit that portion's angular momentum, while the star's equator would record the integrated torques acting on the stellar interior and surface. An inclined stellar companion offers one mathematically developed source of such a torque. A distant companion can pull on the disk and make its angular momentum vector precess around the binary orbital axis. Meanwhile, the oblate rotating protostar and its disk torque one another, causing the stellar spin and disk normal to precess on their own timescales. If those precession frequencies pass through a secular resonance as the disk loses mass, an initially small misalignment can grow. This mechanism has been shown in theoretical models to generate substantial star-disk angles within disk lifetimes, and observations of young binary systems confirm that strongly misaligned disks can exist. But the Sun has no known bound stellar companion today, and invoking one for the early solar system requires an unseen former partner that was later removed, or a close stellar encounter in the Sun's birth environment. Such histories are dynamically possible, especially because the Sun likely formed among other young stars, but no surviving evidence identifies a particular companion or encounter as the cause of the solar obliquity. The mechanism is therefore physically credible without being historically established. Magnetic interaction between the young Sun and the inner disk provides another route. A protostar's magnetic field can thread ionized gas near the disk's inner edge, where differential rotation twists field lines and creates torques capable of changing stellar spin magnitude and direction. When the stellar magnetic axis, rotation axis, and disk normal are not perfectly aligned, magnetic stresses may warp the inner disk or push the stellar spin toward or away from the disk axis, depending on field geometry, accretion rate, conductivity, and the extent to which field lines remain connected rather than opening into winds. The same magnetic coupling can act alongside the gravitational torque produced by the young Sun's rotational bulge. Because the star was larger and more magnetically active during its pre-main sequence life, its quadrupole moment and magnetic environment were unlike those of the quiet modern Sun. Calculations show that these torques can influence primordial spin-orbit alignment, but their direction and efficiency vary enough that they do not yet provide a unique reconstruction of the solar system's 6-degree offset. The interior of the Sun introduces another subtlety. A forming star is not always compelled to rotate as a perfectly rigid body, and accretion deposits angular momentum near the surface, while convection, magnetic fields, and internal waves redistribute it. The present photospheric rotation axis is measured from the modern Sun, whereas the relevant primordial quantity was the angular momentum orientation of a larger, magnetically active protostar. Most models expect strong coupling to keep large internal tilts limited, but the translation from early stellar rotation to the axis observed today is not entirely free of stellar evolution physics. A different family of explanations places the main torque after the planets had already formed. In this picture, the Sun's spin remains nearly fixed in inertial space, while the collective planetary plane slowly tilts around it. Because the Sun contains almost all the solar system's mass, but only a small fraction of its total angular momentum once planetary orbital motion is included, it is dynamically easier for a distant perturber to redirect the planet's orbital angular momentum vector than to tip the entire Sun. This insight motivated studies asking whether a remote, inclined planet could gradually torque the known planets over billions of years. The hypothetical Planet 9 has been shown in secular calculations to be capable, for some ranges of mass and orbit, of generating an obliquity comparable to the observed value, while also influencing distant trans-Neptunian objects. The idea is elegant, because one cause might account for more than one outer system pattern, but elegance is not detection. Planet 9 has not been confirmed. Recent infrared searches have produced candidates requiring follow-up, rather than a verified planet. Large portions of its proposed parameter space have been excluded, and the statistical significance and interpretation of distant object clustering remain debated. It must therefore remain a testable possibility rather than an answer. A post-formation stellar flyby could also torque the planetary system, particularly its outer regions. but an encounter strong enough to create a coherent 6-degree tilt must avoid overexciting the planets, stripping too much distant material, or leaving other signatures inconsistent with the solar system. That narrow balance makes such scenarios informative to simulate, but difficult to establish from present evidence. The smallness of the observed angle itself may be a clue. 6 degrees is large enough to reject perfect alignment, yet small enough that the Sun and planets still clearly share a common rotational origin. It does not demand a catastrophic event. A slightly shifting accretion flow, a gently warped disk, magnetic and gravitational star-disk torques, a temporary companion, a distant planet, or some combination of these processes could each contribute part of the offset. The mechanisms are not mutually exclusive, and the actual history may have involved several modest torques whose effects accumulated rather than one decisive disturbance. What science can state with confidence is narrower and more valuable than a dramatic certainty. The planetary plane and solar equator are measurably misaligned. The basic disk formation model naturally explains their near alignment, and the remaining few degrees preserve information about physics omitted from the simplest symmetric picture. They may record the changing direction of material falling from the Sun's birth cloud, the ability of disks to bend and precess, the magnetic conversation between a young star and its surroundings, or the lingering pull of something distant. The imperfection does not weaken the explanation for why the solar system is flat. It reveals that flatness was never a frozen command imposed at one moment, but an evolving agreement among several reservoirs of angular momentum. The planets remained close to one another's plane because they grew from the same disk, while the Sun's equator and the disk's final plane separated slightly as that young system exchanged mass and torque with its environment. And within this narrow angle, scarcely noticeable beside the vastness of space, the solar system leaves one final message before the story closes. Its flatness is not merely a shape, but the surviving record of which motions were erased, which directions were preserved, and which ancient disturbances were never completely forgotten. The flatness of the solar system is not merely a shape suspended in the present. It is a fossil of motion, the surviving geometry of processes that ended before any planet had acquired its modern name. If we could remove the planets, erase the asteroid belt, dissolve the Kuiper Belt, and look backward through the long sequence of construction, we would not arrive at emptiness, but at a rotating cloud whose most important feature was not its material composition, its temperature, or even its total mass, but the fact that its motions did not cancel perfectly. A small net angular momentum remained after countless turbulent streams were added together, and that residual vector quietly defined an axis around which the future system would organize itself. Gravity then reduced the cloud's size, increasing the importance of rotation as material moved inward. Yet contraction alone could not produce the narrow planetary structure we see today, because a collisionless population can orbit a central mass in 3 dimensions indefinitely. The decisive step was dissipation. Gas streams collided. Shocks converted bulk motion into heat. Turbulence carried energy towards smaller scales. Dust grains transferred momentum through drag, and radiation allowed thermal energy to escape. The cloud could therefore lose the energy associated with random and vertical motion, while retaining the accounting imposed by angular momentum conservation. This asymmetry between what could be forgotten and what had to be preserved, is the deepest physical reason the solar system became flat. Motions directed upward and downward often came in opposing pairs and could be cancelled through interaction. The shared circulation around the central axis did not cancel because most of the material participated in it in the same sense. As the disorder faded, rotation remained, and the cloud settled into a disk whose plane lay perpendicular to its total angular momentum vector. The young sun formed near the center, while matter carrying too much angular momentum to fall directly inward accumulated around it. That disk was never an infinitely thin surface. Thermal pressure, turbulence, magnetic stresses, continued infall, and vertical oscillation gave it a finite thickness, while the balance between pressure and stellar gravity determined how rapidly its density declined above and below the midplane. In the simplest local description, the scale height was set by the sound speed divided by the orbital frequency, so warmer regions remained thicker and cooler regions could settle more closely toward the middle. The gaseous disk therefore preserved a measurable vertical dimension even as it became geometrically thin compared with its radial extent. Within that gas, solid particles underwent a second and more selective flattening. Dust grains oscillated across the midplane, lost energy through aerodynamic drag, and gradually concentrated into a narrower layer, although turbulence continually mixed some of them upward. Their degree of coupling to the gas could be summarized through the Stokes number, which compared the drag-stopping time with the orbital timescale. Tiny grains moved almost as part of the gas. Larger aggregates settled more efficiently and drifted radially as the slightly sub-Keplerian gas applied a headwind. Pressure maxima, vortices, snowline transitions, and other disk structures may have concentrated solids, while streaming instability offered a route by which dense particle filaments could collapse under their own gravity into planetesimals. Whatever combination of mechanisms operated in each region, the durable building blocks of planets were born inside a layer already centered on the disk's plane. They did not begin with random orbital orientations and later submit to a cosmic alignment. Their low inclinations were present at birth because the matter available to construct them had already lost most of its vertical freedom. As planetesimals grew into embryos, the geometry of the disk continued to favor flatness. Bodies on neighboring low-inclination orbits encountered one another more often, and usually at lower relative speeds than objects arriving from steeply tilted paths. Gravitational focusing enlarged the effective capture zones of growing embryos. Dynamical friction reduced some of their random motion, and pebble accretion could become more efficient when the solid layer was thin enough for an embryo's gravitational reach to intercept a substantial fraction of the passing material. Growth inside a disk was therefore not simply growth occurring within a flat background. The flatness actively shaped which encounters happened, how frequently they happened, and whether they ended in merger, scattering, or destruction. The planets inherited the disk's angular momentum through countless acts of addition. Each merger combined bodies already traveling in approximately the same direction, so the resulting object remained close to the common plane. Gas then reinforced this inheritance. Young planets excited spiral density waves, bent the surrounding disk, and exchanged angular momentum through gravitational torques. Inclined embryos crossed dense gas, leaving wakes and transferring vertical orbital energy into a medium capable of spreading and dissipating it. Eccentric motion could be damped in a similar manner. Migration and resonance complicated the process, but while the gas remained abundant, the disk possessed a continuing ability to cool the planetary system dynamically, reducing departures from the plane even as growing worlds perturbed one another. Then the gas faded. Accretion, radiation, winds, and photoevaporation removed the medium that had continually absorbed disorder, and the solar system entered a new age, in which gravity could redistribute orbital energy far more easily than it could erase it. Embryos collided, giant planets migrated, resonances swept through populations of smaller bodies, and close encounters lifted some objects onto inclined or eccentric paths. The planetary system thickened. Mercury acquired a modestly tilted and eccentric orbit. The asteroid belt was stirred into a broad distribution. The Kuiper Belt developed cold and hot populations, and some comets were scattered outward until galactic tides and passing stars could randomize their orientations into the nearly spherical Oort cloud. Yet the massive planets did not become a spherical swarm, because internal scattering could rearrange angular momentum without easily overturning the direction of the total vector. The system's dominant orbital momentum remained concentrated around the original axis. What survived was not the pristine disk, but a wrinkled descendant of it, a structure made thicker by history while still governed by its ancestry. This is why the solar system can contain Pluto on an orbit tilted by about 17 degrees, Eris at roughly 44 degrees, and long-period comets arriving from almost any direction, while the 8 planets continue to trace a narrow shared layer. Small bodies are easier to redirect because they carry little of the system's total angular momentum. Massive planets are far harder to tilt collectively, and their orbits continue to define the old plane even when smaller populations wander far from it. The slight misalignment between the planetary plane and the Sun's equator adds one final nuance. The star and disk nearly agree, as expected from a common origin, but they do not align perfectly. Changing accretion directions, a warped primordial disk, magnetic and gravitational star disk torques, an early companion, or a distant perturber may have contributed, although no single explanation has been established as the unique history. The remaining few degrees do not weaken the disk model. They expose the difference between an idealized symmetric collapse and a real system formed within a turbulent, changing environment. A perfectly aligned solar system would contain less information. Its small imperfections are the fine print of its formation, preserving influences too subtle to erase the larger pattern. We can now answer the original question at several depths without changing its central meaning. The solar system is flat because its planets formed within the same rotating protoplanetary disk. That disk became flat because a collapsing cloud possessed net angular momentum and could dissipate random kinetic energy. It remained only finitely thin because pressure, heat, turbulence, and later gravitational stirring resisted complete flattening. Its plane survived for more than 4.5 billion years because the total orbital angular momentum of the major planets is conserved with extraordinary fidelity, even while individual orbits precess and exchange small amounts of inclination. If the primordial material had been unable to collide, shock, drag, and radiate, there would have been no efficient reason for its inclined motions to disappear, and the resulting system might have remained a thick, three-dimensional swarm. If it had possessed no angular momentum, much more material could have fallen directly toward the center, leaving little extended disk from which planets could form. The planetary system required both properties at once: enough rotation to resist radial collapse, and enough dissipation to remove motion that did not belong to the common circulation. Flatness emerged from that partnership. It is the geometry produced when matter can cool without forgetting how it turns. From a great distance, the orbits may still resemble circles drawn upon an invisible sheet, but the sheet itself is not an object. It is a memory encoded in velocity, a plane defined by the sum of ancient motions, a silent remnant of gas that disappeared billions of years ago. The planets continue to circle within it because they are not visitors placed around the sun after its birth. They are condensed portions of the same vanished flow. Every year, Earth completes another orbit, not merely returning to a location in space, but retracing the direction inherited from the protosolar cloud. Jupiter carries an even larger share of that old rotational memory. Saturn follows, and the smaller worlds move within the same broad agreement. The disk is gone. Its heat has escaped. Its gas has been swallowed or dispersed, and its dust has become planets, moons, asteroids, comets, and living ground beneath our feet. Yet its most enduring feature remains visible in the alignment of the sky. The solar system is flat because nearly everything that once moved against its common rotation was gradually softened, canceled, scattered, or lost, while the shared angular momentum survived. What we see today is therefore not simply an arrangement of worlds, but the outline of a motion that is no longer there, preserved with such patience that even after billions of years, the planets still travel through the shadow of the disk that made them. The solar system's flatness is the quiet memory of the spinning disk that created it. Thank you for listening tonight, and please subscribe to Sleepy Space for more calm journeys through the universe.